I'm re-uploading this video just because there were some problems in the previous video. So my apologies, I'm sorry for that. Let's jump into the video. Welcome back. In the series of creating chatbot from scratch, I'm going to add this part 4, and in this video we are going to see how to build encoder decoder model. But before, let's quickly see how this model looks like and how it works. Alright, so let's start from the user end. First of all, user gives the input and then it is fed into the embedding layer. We would later see what this embedding layer do. Then this is sent to the LSTM network, and LSTM creates the context from that vector, and that context is known as states or internal states of that model. Then those states are sent to the decoder model with the SOS or any particular token, and then it predicts the next word, and that next word is transferred to the decoder, and then again it predicts the next word, and this cycle continues and this goes on. And now let's quickly see what we have done in our previous 3 parts. And in the previous 3 parts we have done all the data pre-processing we need, and now we have the data which is ready to be transferred to our model. If you don't know, please go ahead and watch those 3 parts because those are super necessary for this part. First of all, let us quickly make some normal imports like dance layer and LSM layer. These are obvious, we need to import them. And embedding layer, I will explain you later when we will use this embedding layer. And one thing you might notice is that I'm importing model instead of sequential. This is because model is a functional approach, and this gives us more control in our hands to optimize the layers or to use the layers wherever we want, like we will need them during the inference. And so we are going to use functional approach instead of sequential approach. One thing I forgot to do in pre-processing part is adding this to categorical function to this decoder final output variable. What this do is it converts the 2D data to 3D, which is expected for LSTM output. It creates a separate column for every word in the vocabulary to the decoder final output variable. It creates a 3D matrix of so many zeros and so many ones. You can run this and see this. Alright, so once you have made all the necessary imports, let's create an input placeholder for encoder and decoder. And we would simply do by using saying input and giving it shape as a tuple, and in that we will pass 13 comma none, and 13 means the length of input which we are going to pass in. So we will do this same for decoder. It basically holds the value which we are going to pass during the runtime or during the training time. Alright, so now let's quickly create an embedding layer. Embedding layer generally reduces the dimensionality. We pass in input dimension, which is the length of the vocabulary, and we need to give it a output dimension which we want to reduce. So for example, in our case vocabulary size would be 3000, so it will going to compress that into just 50 values, 3000 values to 50 values, so it reduces the dimensionality. And we just give it 3 parameters. One is input dimension, output dimension, and input length. This is the length which we are going to give it during the runtime, and that is it. Now let me give you a quick example. Okay, so as in our case, the input shape would be a 20,13, which is 20 is the number of the samples which we are going to pass in length of question and answers, and 13 is the length of one question or one answer. So once we pass this to embedding layer, this would give us 20, 13, 50. 50 the output dimension which we have set later when we were defining embedding layer. So quickly, why do we need to convert our 2D data to 3D? This is because LSTM expects the 3D data. So this is it for embedding. If you want further reading, I will link down this resource. And now it's time to connect our encoder decoder placeholders with the embedding layer. It is as simple as just passing in them these braces. We will just say embedding and that braces and encoder input, and we would later on do the same for decoder input. And now let's quickly create a encoder LSTM layer by simply saying LSTM, and we'll name this as ENC LSTM. And the first parameter is the number of cells, LSTM cell. We will pass 400 for now, and it takes return state equals to true and return sequence equals to true. Return sequence generally returns the hidden state at every time step, and return state returns the hidden state and the cell state at the last time step. If you want further reading, go in the description, and I would link best reading which I found for this explanation. So now we will connect this LSTM layer with the encoder embedding in order to access the encoder output H and C. We are able to access H and C due to return state equals to true, return sequence equals to true. So you need to set them to true if you want them. And now at last we will just create list of H and C by just saying passing them to a list. And now let's add decoder LSTM. it is just similar to encoder LSTM cell, but the thing is different is that we will use encoder state as its initial state of decoder LSTM, as you can see in the diagram. And one more thing we have to change is going above in the vocabulary size, we have to add 1 instead of reducing 1. This is because we are adding pad token extra in our vocabulary, so we have to tell it by specifying +1 in the vocabulary. And now let's create a dense layer by just simply saying dense and name this as the small d dense, and it will going to output the probabilities equals to the vocabulary size. And obviously we need probability, so we will use the softmax activation function. Now we have dense layer. Now we will connect this dense layer with the decoder output in order to get the final dense output. And now it's time to finally wrap everything up. We'll use model class in order to create model, and we have already imported. So now it takes 2 arguments or 2 values, which is input data and the output data. Input data is obviously encoder input and the decoder input, and the output data is the final dense output. So let's quickly replace them up. And now at last we will compile our model by saying model.compile and setting the Adam optimizer and categorical cross entropy as a loss. And now at last we will fit our model on our preprocessed data. And if you don't know how to preprocess data, go ahead and watch previous 3 parts, and we know we had encoder input, decoder input and decoder final output as our preprocessed data. So now let's quickly replace them up, and we will use 40 epochs for now. Now to run this code, I will jump to Kaggle because my laptop is not too powerful. I will copy the code which we have just coded and that previous 3 part code, pre-processing code over here. As I've told you that vocabulary size, so we will use length of vocabulary, and that is it. Let's quickly run them up, and for now I will just use 2 epochs just to show you that it works. And at last, to use this model we would have to create inference, and this is something we are going to do in the next part. And if you are wondering that why I didn't use attention layer, and this is because I don't want to make this part complex, so we will create attention layer in the future parts, but for now, for keeping the things simple, I will just go with this simple model. And I would like to stop this video at this point. If you think that I am able to give you something useful, please make sure you give this video a thumb up, and I will see you in the next video.